Hey everybody, Ajax here. I got another tutorial for you guys. Um, After the last video, which is about 2 months ago, I've actually been having a hard time trying to figure out what video I wanted to do next. We've done a lot of relatively simple ones. I wasn't really sure what direction to take the channel in terms of continuing to kind of give entry level, here's how you make a simple game, here's how you kind of think about it. I did have a request following the last video, which was on Unity. And it was, let me see if I can pull that up here, by, I think, Bhagawan Lalith. I'm pronouncing that terribly, my apologies. However, the question was, can you bring out tutorials on networking and multiplayer games rather than 3D ones? And at the time I replied and I said, basically, I don't know that that's going to happen anytime soon. And the reason being, as soon as you introduce multiplayer into a game, the complexity of the logic becomes enhanced, and you have a lot more issues you had to think about. The other concern that I had is it had been a very long time since I'd done any sort of like multiplayer game development. I do some asynchronous networking development in my day job, but that's related around HTTP requests and REST protocols and things like that. And a lot of the tools that are already created for that abstract that away to the point where you're not really dealing with really low-level stuff. So last 2 months, I've been thinking, trying to figure out what video we're going to do. And I kind of took this request as a challenge, and it's been stewing in the back of my mind, and I've decided that what we're going to go with, we're going to make Tic-Tac-Toe, and we're going to make it multiplayer. I was thinking about it, I'm like, what's the simplest possible game, the fewest variables I can think of? Tic-Tac-Toe is a very simple game, right? You have a grid, it's 3 by 3, you place an X, your buddy places an O, if one of you gets 3 in a row, you win. Plain and simple. There's not a whole lot of things going on. There's no like real-time action like with Pong or Breakout. You don't have to really handle user input at that level. So I was like, okay, that'll simplify things. And then I was like, okay, so I should be using Python 3, right? I've been using Python 2 before, but Python 3, it's gotten to the point libraries have, been ported over, or if they're not porting over, a lot of them are kind of dead. Some of them are not, but I wanted to go start doing Python 3. So for this, we're using Python 3. Now, when I was looking at networking, like for a multiplayer game in Python 3, I went back to what I knew originally, and I kind of built up from there. You can see over here on the side here, I did actually a substantial amount of prep for this episode, a lot more than I normally do, because it was a subject that I haven't done in a while, and I knew it was going to be such a complex one. And so there's a few caveats that I really want to call out before we dive into actually coding this game. All right. So the first one is that none of this should be necessarily taken as the best way to do it. This should be taken as here's an introduction to some of the things you should be thinking about when you're doing a multiplayer game. This will function and this will run, but it's not necessarily going to be the most optimized or secure or whatever issues you will run into if you try and actually build a game yourself using these concepts. The second caveat is I'm using a library called Asyncio, which is a core library in Python 3.4 and up, I believe it is. So get a recent version of Python 3 and you'll have Asyncio. But this library, what it does is it provides a relatively high-level abstraction, a concept of an event loop, and then inside that event loop, it has an abstraction around the network message passing that is higher level than the types of networking that I had done before. So I have only used this Asyncio library for about a week and a half. So I'm also nowhere near an expert on the library itself. But it does simplify things enough that I think it's worth using that. There are some other alternatives. You can go down to raw sockets and use something like select to figure out which sockets are ready for reading and writing, but that's really low level. And I did a version of this where I implemented the game using sockets and select. I just thought there was way more information that I had to kind of explain, which isn't necessarily a bad thing, but it's just too much of a dive to do in this format, I think. Maybe if we want to do a deeper dive later and do like a series of them, maybe something like that then, but not for this. The other one that I had used before is called Twisted. Twisted is a networking suite, if you will, for Python that has tons and tons of libraries inside of it. If you want to connect to, ERC or HTTP, like websites or chat rooms or websites or FTP or like file storage servers, it has stuff to handle all of that, but it's not fully ported for Python 3 yet. I think enough of it's there that you could use it if you're interested in trying. It's a very, very well-known, very stable library, but I've always found the amount of boilerplate there to be very high, and looking at it, it seems like Asyncio is just a cleaner way of doing a lot of the stuff that we would be doing with Twisted. So with those caveats in mind, let's go ahead and get started. So what we're going to do today is a little bit different than I've done before. I guess this should probably have been part of the caveats, but before I really just kind of coded from the hip with a concept in my head, and we just built it up. So you got to see the process that I went through of thinking about how I wanted to do something, implementing it, testing it, debugging it, and making it all work. For this, because it is such a kind of in-depth concept, I actually went ahead and I built the entire game out ahead of time in the final version, and we're going to be referencing that. And what we're going to do is we're going to basically re-implement all of the stuff that I did in the preparation. So we'll still go through it the code line by line, but because it's all basically figured out, we won't see it necessarily having the same number of bugs and issues that I need to work through. So if you're more interested in seeing that type of coding, please look at my older videos, even if they are old and dated and I don't know as much in them. They could be very interesting. So we're going to go ahead and we're going to start our project. So we have a prep project over here on the left. This is what I started with. In here, we have a game.py and a server.py. Basically, you run the server if you want to be a server, and then each of the players starts the game and runs it. And then inside the library, or lib, we have our grid. So this represents the tic-tac-toe board. We have the net, this would be all of our networking code. So this is basically wrapping all of that to try and make it as high level as we can. And the UI. So basically, we split it up into as much of the functional stuff and individual things as we can. So let's go ahead and let's do that. So we're going to create a folder called lib inside our tic-tac-toe directory. And inside lib, we're going to create a file, which is init.py. So init.py is a special file in Python. Normally, it doesn't need any contents. Sometimes you'll put contents in there if you want to change the way that you're exposing them. But what this does is it basically lets Python treat this whole folder and all the Python files inside of it as a module. So you can say from lib import, well, let's make a file, net. So you could say from lib import net, and this allows that to happen, and everything in net you can then use. So it's a really handy way of organizing your files, so that similar pieces of code can go together without blowing up into a single flat directory where everything's together. So we're going to make these three files. So grid.py and UI.py. And then in the base directory, we're going to create server.py, and we're going to create game.py. So before we get started implementing this, let's look exactly how this works. So I'm on Windows, which is not necessarily ideal for this type of development, but I'm here, and I'm assuming a lot of you probably are. So I have actually installed Bash onto Windows, which basically just lets you do Unix style terminal programming. So you can do things like CD and ls and such. You can perfectly fine use the Windows command prompt and then CD where you want to go. So you can so I have this in a different volume. So I'm in D, so I can do that. So I can CD to myprogs / let's make a game, and then is it dir, and then cd into ep.7 dash multiplayer tic-tac-toe. So then you're in there and dir, and you can run these the same way once you're in there. So you could call Python server.py and it will run that for you. I'm not using that because I do prefer running it through Bash when I'm working on Windows, but you can certainly do that. So if we cd into the prep directory, I'm going to cd in with all three of these, and we're going to start the server with this one. What? Got to go in one more directory. So Python server.py. So this is going to run the server, which isn't going to do anything at the moment. And we're going to say game.py. So we're going to start up one copy of the game. And so this is basically the game that we have right now. You see the grid. It says we're waiting. We're waiting for the other player. They're not here. I have 0 wins, 0 losses, and 0 ties. So over here, the server's like, oh, we have a player. Cool, we have one player. So we start another version, another instance of the game client. And now we have 2, and now it says starting. And then after a second, it says playing. So the game starts. So this player is X, this player is O. It's not this player's turn because he doesn't have anything highlighted. He can't do anything. So player 2 over here, right? So I'll stick this up here to keep track. So you can move around with the arrow keys, and then enter lets you select a choice. Now it's not longer his turn. Now it is O's turn. So O can play like here, and X is like, oh, okay, so I'm on a filled square. It's red. Green squares are open. So let's say that, you know, normally in tic-tac-toe, you're almost always going to have a tie, but let's say we want this character, this player, to win. So this player is just going to go something stupid instead of going down here to win. This one does. Now, there's going to be, as with some of the earlier versions, there's going to be some places for you to take the code and enhance it. So one of them is, right now it's just printing out you lose or you won or you tied, and then the game's over, and it shows you your number of wins and losses. But it doesn't actually give you a countdown between games starting and ending, and it doesn't actually show any sort of you won screen. So that's going to be something that you can work on adding yourself. So don't worry about that being missed too much. So this is the basic game we have right here. A player leaves, and since it goes back to waiting for player, there's actually a little bug here where it says, oh, hey, we're playing, even though we're waiting for a player, which isn't true. So we'll have to maybe address that in the actual version. So that is the game, for now, that we're going to emulate. So the first thing we're going to do is we're going to start from the ground up. So we have the game and we have the server. We're not going to start there because those build upon everything else that we're doing. We're going to start with the grid. The grid is what represents the playing board, right? So the grid is very, very simple. So what we're going to do is actually we're going to have this right here. So we're going to go through what this does, and then we'll implement it over in the other window. Okay? So we're creating a class, which is just a type of a description of an object, basically. So when you invoke this class, you'll get an instance of it. When we initialize the class object, we want to call reset. Reset basically sets ourselves to be a list of lists with empty strings. Empty strings represent an empty cell, and X represents an X is there and an O for no. So what we're doing is we're using list comprehensions here. So a list comprehension, it basically says create a list for all the items in the thing that you're doing. So what we're doing is saying for range 3, so that'll give us 0, 1, and 2. So we're basically saying for Y in range, create a string and create that as our list. So we're creating a list with 3 strings. And then we have an outer one that is saying do that 3 more times. So then what we end up having is something equivalent to this, basically. So you end up with a array that has 3 rows, and in those rows you have 3 columns. So that's first. So let's come over here and let's start doing it. So class grid, define init self.reset. So def reset self.cells equals, so a string for y in range 3 for x in range 3. Doing it this way also lets us basically say self.cells x, y, and get the value at the cells. So we have that right there. Okay. Check free. So check free is a function right here. It's a helper function. We basically are just saying, hey, at this x and this y is the cell free, right? This is just a helper function because the actual check is pretty small, but it's pretty simple. Return self.cells x, y. So this returns the string at that specific position. So this just says, hey, return whether or not it equals an empty string. So if it's x or o, it's going to return false. If it's an empty string, it'll return true. Update value. So update value is going to check whether we're free or not. And if we're not free, it's going to return false. So what we're doing here is rather than throwing an error, if you try and set a value that is already filled, set a cell that's already filled, we're going to return false. That way it can be handled more cleanly. So this is one of the things that with multiplayer, I've always noticed myself erring towards a lot more. With single player, I was always fine with basically throwing a exception or handling things a little differently if it was something bad like that. Actually, I really shouldn't say that because I shouldn't say that because this is just better to do in general. Because if you're in game like we were and you're moving around and you tried to hit enter on a cell that was already filled, you just don't want it to do anything in that case. But I digress. So we're checking if we're free. If we're not free, returning false, which basically says the update did nothing. If that doesn't happen, it's going to continue executing, and it's basically going to say my cells at x and y equals the value. And we're going to return true, which indicates that we did the change properly. So, y value. If not, self.check free xy, return false. You could put this in an else and just say self.cells x, y equals value, return true. However, it's basically equivalent to just do this right here, logically, because if you return here, it short circuits out the function, so this will never get called. If this doesn't short circuit, then it just runs. So they're perfectly equivalent. It's just a few characters less. Update from cells. So what this allows us to do is just pass in a new definition of cells. So a new array of the same format. And it just replaces our old array. We're going to use this later on for the server to allow. Basically, what we're going to have it do is when you make a play, you're not actually going to change anything in your game. You're going to send a command to the server. The server's either going to accept the move or not accept the move. And if it accepts the move, it'll update the cell, and it will just send the whole definition of the cell, of the grid, back to each player for them to update. So you don't have to worry about any sort of potential desync of that. Okay, so now we're getting into some interesting logic that is a little bit harder to read, but I'll try and explain it as simply as I can. or as clearly as I can. So basically, it's easiest to start with game over. So the game over is a function that returns x or y. Why would it be x or y? It's x or o. Yeah, it's x or o. So it returns x or o if one of them won. So if x has a line 3 across, then they win. If o has one up and down, they win, right? Or the string tie if all of the cells are filled in and no one has won. Or false if not. So basically, if not game over, you continue playing. If game over, you look at the value of game over to figure out who won or if it's a tie. So what we do is we define what the winning groups are. So winning groups represent a group of cells that if they are all the same value and they're not blank, so that all of them are X or all of them are O, you win. So it could be the top row, it could be the second row, it could be the third row, it could be the first column, it could be the second column, it could be the third column. It could also be on the diagonal. So it could be the top left, middle, and bottom right, or it could be the top right, middle, and bottom left. So those are the only winning situations that you can have in Tic-Tac-Toe. So it's a little bit of a brute force method of figuring it out, but that's part of why we went with such a simple game. So what we do is we go through those. So we take each of these groups. So for group and win groups, this would represent this single group, for instance. And then after that one goes, it'll be this one. So that's what we're doing. We're just looping over each of them and setting the value of each one to group. Side equals self to check group win group. If side, so basically if a win happened, we return that side won. If we did not, so if you return here, it short circuits out, the function is over, somebody won, it's going to be X or O. If none of these groups won, then the function will continue down. And we'll go to the second one. The second check here is saying, okay, let's check if there are any free cells left. So it goes through each of these cells for X in range 3, Y in range 3. If not self.cells XY, return false. So this actually would be better written now that we have this check free function. So it'd be like if self.check free XY, return false. So if that cell is free, then we're saying no one won. So that's this condition. Game over is false. It's still playing. If this loop has finished and it hasn't found a free slot, that means there are no free slots left. No one has won. It is now a tie. So the next part of this function is the self.check group win. So for each of these groups, we're calling another function to evaluate whether or not that group is a winning group. So that's this check group win. So what this does is it sets a value to none. The value is going to enter or equal the first value in the group. So it's easier to explain as we go here. So for cell in group, so for each of these groups, cell is going to first be this cell, which would be the top left, this cell, which would be the middle top. Or actually, this is X, Y. Okay, so this would be the left side middle, left side bottom. So cell is going to equal each of those, and we're going to loop through them. So the X and the Y is the cell, so X and Y. And then side equals so this is the value of the cell. So side would be X if you're the X player, Y or O if you're the O player, or empty string if it is not set. So what we do then is we say, okay, for the first cell in the group, value is none. So we're just going to set value to whatever is in that first cell. Okay? Otherwise, we check whether the current cell has the same value as that first cell. If it does not have the same value, then this group is not a winning group. So it's the same as if all of the cells were empty, basically. If that loop fails, it doesn't end up finding a non-different, then it means all of the values are the same. And that might mean they're all empty, or they're all X, or they're all O. So we're simply going to return whichever one that it is. So the top level, we're going through here, we're basically saying, for a set group of cells, evaluate whether or not the value of all of those is the same. If it's different, then it's as if, then no one won that, basically. Basically, what we're returning from this is X, O, or blank string. If an X or an O are there, you won. If it's a blank string, you haven't won yet. Or there is no winner. So that's what check win group is doing. So I think we can actually make this a little bit clearer. So let's go ahead and do that. So def check win group self comma cells. This is basically we're sending in a group of cells. So cell group. So we're going to do this to be a little clearer. This is be a slightly less optimized, perhaps, because you're pushing things onto a list or appending things onto a list, but who really cares? For cell in cell group, X comma Y equals cell values dot append self.cells x, y. So this is much simpler than the other code that I was working against, even if it's a little less perhaps performant, but we only have ever 3 items at most in here, so who cares? So what we're going to do is just say, so what we can do is actually say, oh, wait here. If not, so let's just do value. So value equals self.cells x, y. If not value in values, values dot append value. So what we do is we're going to say, okay, if len values equals 1, return values 0, else we're just going to return empty string. Actually, we can just return false. No, empty string. Interesting. Empty string. So the reason we're doing that is because if all of them are empty, it would be an empty string, so we want to just assume empty string means nothing on it. So what this is going to do is actually it's going to do exactly the same thing. It's going to go through this group of cells, and it's going to get all of the values. And then it's going to put unique values into this array, or list. Into this list. And what's going to end up happening is that if all of them are X, then the second and third cells are going to see that their values already in values, and they won't put in there. So we'll get down here, and basically if they're all the same, you'll see len values equals 1, which means they're all the same, just return that value, which is the first value. Otherwise, we say they're not the same, and we return an empty string, which means the group didn't win. All right. Clean that up a little bit here. So we're going to say next, let's go back to the game over. Def game over self. And win groups equals this. So we're going to define our winning groups again. So in here, we're going to say that first we have 0, 0, so top left. And then we're going to say 1, 0 is top middle, and 2, 0 is top left. So that's a potential winner. We're going to duplicate that just for simplicity's sake. And we're going to come down 1 in our columns and say, okay, middle left, middle middle, and middle right are a potential winning group. And we're going to duplicate it again and say, okay, here's all 2. So this is going to say bottom left, bottom middle, and bottom right. Then we have another group, which is going to say also in the top left is where this one starts. But then we go to the left side middle left, I guess. And we go to middle bottom. So left side at the bottom, or left bottom, sorry. And then we'll duplicate that again, and we're going to say, okay, so second row. Second column. So x equals 1, so that's now in the middle. So middle top, middle, and middle bottom. And then last but not least, we have bottom left, bottom middle, bottom right. Then we have our crisscrossing ones. So crisscross is pretty simple. We say top left, middle, bottom right. And we also have top right, middle, bottom left. There's our winning groups. They should be the exact same as these, just slightly different order, perhaps. 0, 2, 1, 1. Yeah. Slightly different order. Let's see here. Yeah, so I switched the order of them as I was doing it for some reason. So we're going to go through our winning groups and see if any of those won. So for cell group in win groups, if, let me see here, side equals self.check win group, cell group, if side, return side. So again, if side is X or O, one of those two won, so we'll just return whichever one won. Otherwise, they haven't won because it's blank or there are different values, so we're just going to pass. Now, we're going to check if we have any empty cells. So for X in range 3, for Y in range 3, if self.check free XY return false. So what we're saying, if none of our winning ones are finished, and if any of our cells are free, the game is not over. You just have to make another play. Otherwise, if we have done all of that and we have not found any open cells, we haven't found any winning moves, it is a tie and the game should be over. So there is our grid. All right. Fairly simple. I need to pick up the pace a little bit. So I'm noticing it's already about half an hour in. Spent the first 10 minutes talking, but we're at about 20 minutes on just going through grid and just describing how this works. And this is like the simplest part. So I'm going to pick up the pace a little bit in terms of, I'm not going to explain everything in quite the same level of detail. Hopefully there's no issues. If there are, as always, feel free to ask in the comments, or I think I'll link the forum below. It's been a while since I've done this, but you can reach out to me and I'll see if I can help. All right, so we have our grid. We're going to go down. We're going to do the net next. So the networking part, this is really the biggest part. Once this is in, the rest of this kind of starts to flow really quickly. So let's close our grid for now and let's look at the two versions of net. So this is the prepared version. So what we are going to do is we're going to use Asyncio to manage our connection. We're going to send messages from the server to the client using JSON. So JSON is a text format which basically allows you to encode data. It's a data format. And so what we can do is we can convert dicts and lists and all sorts of different types of Python primitive objects into a string that we can send. And we're going to use that to basically generate commands that are sent from the server to the client or the client to the server, and make it very easy for us to write handlers that handle those commands and do things without having to like check each message and parse it and figure all that out. So in Asyncio, there's a concept of a protocol. What a protocol does is it basically is a wrapper around a connection and is the definition for how you communicate on that connection. So in this case, we are using it to automatically encode or decode JSON messages. So first and foremost, we're going to say that a JSON protocol is going to inherit from asyncio.protocol, which actually should do that. Super.init is basically going to call the initialize method from asyncio.protocol and any setup that it does. I don't think it does a whole lot, which is why it really didn't matter that I didn't have that, but better safe than sorry. So we're going to subclass asyncio.protocol, and we're going to want to take a handler. So a handler is going to be our own concept that we're going to write, which allows us to basically define how we want to handle the connection this protocol represents. And I'll explain more about what that looks like, but basically when you get to the server, your actual server ends up being a handler with functions that are called from the protocol, like allow connection or handle a connection made, which means we have a new player, connection lost when somebody leaves, etc., etc. So we take a handler and we just store our handler. We also use the ID function to get a unique ID for this connection. This is primarily used for the server so that it can easily remember which connection has what information associated with it, and we're going to use that to wrap in a player. So a player is a connection, so whenever a message comes in, we'll be able to look up which player is associated with that connection and do something with that information. We're defining a separator. So going back to what I was talking about at the beginning with the caveats. Low-level networking is going to be based upon sockets. Sockets are byte streams. So you might send a message through the socket. You might send hello world as a message through the socket. But if you send a second message through that socket, let's say you're funny, what's going to happen is one of two things. Actually, one of several things, right? So on the server, so let's say the client sends hello world, and then client sends you are funny. The server isn't going to read two messages. Instead, it's going to read a stream of bytes. So however many bytes have been transmitted across the network from your computer to their computer, it's going to read. So the server might see that. But the server might also see just see this, because maybe you sent both of those fast enough that one read just grabbed all of that. There was no waiting time on the network. Or maybe your connection is really slow for some reason, and it only gets hello, and then it gets world, depending on how much it's reading at a time. So because of that, you need a way of indicating from one end of the connection to the other end when a message is completed. So the way that we are doing that is we are defining a separator. So when we use the JSON module, which is in the Python standard library, so when we call json.dumps, we're giving it an object and it's converting that into the JSON string format. And one of the things it's doing is it's escaping any new lines that might be in there that we're giving it, because JSON by default doesn't support new lines. So, right, you can create a JSON document that has new lines for prettyfying, but the Python new line generator does not, unless you tell it to, does not generate the strings, the JSON strings with those pretty new lines. So because of that, we can actually just put a /n, a new line, at the end of each JSON block, and we can split on that, and we know that each one is guaranteed to be a full JSON string, and can be loaded up. All right. We have a buffer. So a buffer, again, is the other part of what we were looking at a minute ago with the byte stream. Maybe you don't get the full message in the first read. If you don't see that new line separator, then you don't have a complete message, so your parsing isn't going to work. So instead, what we're going to do is we're going to store the message on the buffer, and we're only going to pull it off the buffer when we know that we have a complete message. And then we have a rejected flag. This is an internal housekeeping one, which basically lets us say, if we want to have a max of 2 connections, right? We can only have 2 players. If a third player tries to connect, we're going to just reject them. This is a flag that lets us track that we did that, so we don't bombard our handler with, client joined, client left, all this different information. It will only get the, hey, can the client join message. It will never get the connection made or connection lost. So it's just basically a way of making the handler not have to be aware of all that. All right. So we're going to go ahead and we're going to implement this really quick. So import asyncio, import JSON, class JSON protocol from asyncio.protocol. And then we've got a handler. Yep. Okay. Next function, reject connection. This is what we will call if the connection tries to be made and the handler says, no, I don't want to accept it. So basically what we're going to do is we're going to write to our, so the transport comes in. So what asyncio does is it creates a protocol object for each connection. And inside the protocol, when the connection is made, it passes a transport. A transport is a wrapper around that socket that handles the actual network communication. So we will have a transport once the connection is made. So we're going to tell our transport, so basically we're going to write to our socket, which is going to send it over to the other side of the connection. And we're going to say message rejected. So we're going to send through a JSON object as a byte string. That's what that B is doing. And we're saying, okay, reject you. We're closing our connection and we're setting our rejected flag to true so we can check that later so we don't actually, spam out the handler like we were talking about. So, event handlers, this really shouldn't be an event handler, should it? It should be I guess so. Reject connection self. So self.transport.write. Again, we're going to send a byte string. So it's a different type of string from the normal string. It doesn't have the UTF encoding. It's just a stream of bytes. So we're going to send a valid JSON object. So we're just going to send a JSON object that says message rejected. And we're going to say self.close. We're going to set self.rejected equals true. Okay, so we're calling self.close, so we should make sure that we have that. I think it's right. Yeah. Okay, so what this is doing, this is a interesting part of asyncio on Windows. So on Windows, there's a slight bug. Normally, I would write self.transport.close, which would just close the connection. On Windows, that doesn't appear to actually be working well. It ends up throwing an error when it's trying to select on something that isn't a socket. It's very cryptic, and it's hard to understand if you don't know what's going on. So when we call self.transport.write EOF, what that actually does is it tells asyncio that we've reached the end of the line for this socket. If there are any writes, so for instance our write here where we're trying to write this, if there are any buffered writes, it will send those, but it will no longer accept data. And what's the final message has been written, it will close up the socket and make sure everything shuts down in a clean way without errors. So we're using that here to make sure that that happens. All right, so we have our reject connection. So now let's do a connection made. So connection made, this is called by Asyncio with a transport telling you, hey, someone new connected. Here's the transport that represents the communication that you can have with them. So self.transport equals transport. Now, what we're going to do is we're going to invoke into our handler and basically ask our handler whether or not it wants to let us have another thing connect. So if self.handler.isServer. So we could have two types of handlers, right? We have a server and we have clients. The only one that's going to be rejecting connections is going to be the server, because the server is going to be listening to multiple ports. On our client is connecting to a server. That's the only other connection that it has. It's not listening for other connections, so it's never going to need to be checked here. So if it's a server, and not self.handler.allow connection self. So what we're doing is we're passing ourself to the handler and asking if it's going to allow us to connect. Now, the reason we're doing that is later on when we start doing anything else, we're always sending the connection to the handler so it can check the ID and keep track of what's doing what. So we're starting that pattern here. So we're passing ourselves to the function so it knows what connection is coming. So maybe it wants to look up the address of the connection. You know, some games might want to do that. Or maybe it's looking up, you know, the ping against the connection. Well, maybe it wants to, talk and communicate with that before it figures out whether or not it wants to allow the connection. You know, whatever the case may be. Maybe it wants to look something up, make sure it's an allowed IP, right? Whatever the case, we're passing the connection there in case that the handler wants it. When we say not self.handler allow connection, we're basically saying it returned false. It says no connection. So what we're going to do is we're going to call self.reject connection, and we're going to return. Actually, well, we're going to return. Then what we're going to say is, otherwise, we have made a connection. So we're going to let the handler, use it. So this is slightly different. We're going to say self.handler.handle connection made. Self. So this looks very similar to this function, but its purpose is different, because this function, again, won't be called if this is a client. So because it won't be called if this is a client, we're going to call this one, which is for different uses. So basically, this is just for logic, telling us whether or not to accept the connection. Once the connection is accepted or not rejected, then we announce to the handler, and we tell it, okay, a new connection has been made, here you go. Now, you could wrap this up into the same thing. You could basically check the value of handle connection made, and if it returns false, it would close and write something. Like basically, you could do all of that in your handler and not do this rejection logic. But for now, I thought it made the most sense and was simplest to just do it here. But yeah, okay, so if connection has been made, we have a new user. So now we are getting pretty close to having a working protocol. The other thing that we need for a working protocol is we need to handle when the connection is lost. So define connection lost, self. So if our remote goes away, so if we're connected to the server and we lose connection, or if we are the server and the client loses connection, this will be what lets us know that it's gone. And so the only problem with this is when we call close and we write the end of file, it will actually call connection lost eventually. But because we haven't actually told the handler to handle this connection made, we don't want to tell it to handle the connection's lost. So we check if not self.rejected, self.handler.handle connection lost self. So we're basically saying this connection is going away, or it has gone away. I'm letting you know. So there's our connect and disconnect logic. Very simple. Next is data received. So this is called by async.io when our transport receives data from the connection. So the data, again, is in byte strings, so we need to decode it. So self.buff plus equals data.decode. So we're decoding that data, so we're turning it from a byte string into a normal string so that we can check our separator and store it in our buffer, which is a regular string. Then what we need is we need to say, okay, I want to know what the individual messages were. So messages equals self.parse buffer. We'll make that an internal function, or flag it that way, basically. And then for message in messages, self.handler.handle message. Plain and simple, we'll implement this in a minute. What we're saying is each of the messages, so using the separator, everything goes into one buffer, but eventually it gets resolved into individual messages. So each one of those, handle it individually. Parse buffer. So what this does is it's going to look at our buffer. Okay? So what this is doing is saying split our buffer on our separator. And if our buffer ends with the separator, it means that all of the data in the buffer are complete messages. We can send everything, and we set the buffer to nothing. Otherwise, if it wasn't the last, then we know that the last message has not been finished. So we set the buffer to the last message, and all the messages before that are the ones that we're actually going to return that are complete. Then what we're returning is json.loadS message. So this is going to convert the message basically into a dictionary or other Python object if we were sending other ones. In our case, we're only sending dictionaries, but it's going to parse that into a dictionary for each message if it's a message. So when you do split on separator, sometimes you'll get empty strings at the boundaries of where the split happened. So if the new line separator is at the end and you do a split on it, you'll see two values, but the second value will be an empty string. So we just want to just ignore those, basically. So we're just going to implement that over here again. So messages equals self.buff.split self.separator. So this is one of the areas that you could definitely optimize it a fair bit, where you're not just arbitrarily adding all data onto the buffer and then splitting the whole buffer and then resetting the buffer. But for simplicity's sake, we're going to use this way because it's perfectly fast enough for a game such as Tic-Tac-Toe. And if you want to try something a little more full-featured, go for it. So for if self.buff.ends with self.separator, self.buff equals empty, else self.buff equals messages -1, so that grabs the last message, and messages equals messages to -1, that basically says all but the last messages. So return json.loadS message for message in messages. So each message from the messages, if that message, and if it's an empty string, it will be falsy. So this basically checks if that's not an empty message. Okay. So there's our data received. So this is all of the handling of someone sending us information. Now we're going to add our other command, which is to send a message. So if we want to send a message to the other end of the connection, we're going to take our message, we're going to dump it with JSON into a string, and then we're going to call self.transport.write. And so I'm using an F string. An F string basically is a little bit of fanciness that lets you do formatting inside of it. So this here, so inside the curly brace, I have data, data is the data here. So basically whatever JSON.dump_s does is stored in data, and we're just putting the data as the first part of the string, and we're putting our separator immediately after that. So this lets us just do it in a relatively clean way instead of saying data plus self.separator or something like that. But you could perfectly fine use that if you prefer. And then we're calling encode on that string. So we need to convert this regular string into a byte string. So we use encode to do that, and then we send that along the transport to the other end of the connection. Oops. Okay, cool. So data equals JSON.dump_s message self.transport.write f string. And you know what? We're just going to do this. We're just going to do data plus self.separator because it's shorter and it's very clear what that's doing. Actually, no, we're not, because encoding, that's a pain in the butt because then you have to wrap it in other stuff. So we're just going to do this. So data self.separator, boom, dot encode into a byte string, and now that is on its way. So if we send any message, it's going to handle it perfectly fine. So this is our base protocol. This is handling the rules basically surrounding our communication to make sure it makes sense. Next, we're going to define a handler, which is basically, okay, what does the basic handler look like that would, do something for us? So our handler in our case does two things. The first is it handles network communication. The second is it runs our main loop. So when you're doing network connections, you have to figure out how you want to run the loop of your program. In the other games that we did, we simply did while true, like this, do a bunch of stuff. But the problem with doing it that way is whenever you need to read something from the other end, from the network, you have to pause the execution of your program and basically call read until it comes. So if you have a slow connection, every connection has a bit of ping, right? So if you have 100 ping to the server, you're going to wait that 100 milliseconds to get the message before you can even process the message or accept user input or update the display, and everything's going to get really choppy. So what Asyncio does is it builds out a platform that lets you run a loop and then pause the loop and let other stuff run in the background. And the cool thing about that is when network communication is happening, that can happen at the same time as your loop is running in the background, and it only takes control of the loop when there's actual data there for you to process. So you're not waiting on the ping between you and the other server to get your message. You are doing all of your other stuff, and when that message is ready, then you're processing it. So our handler defines functions for each of those callbacks that we defined up above. So self.handler that allow connection, self.handler.connection made, connection lost, and handle message. Right? So that's what this does here. Allow connection, handle connection made, handle message, handle connection lost, and then it does this the part for the loop. So we define the switch. So what switch does is it wraps around a function in Asyncio called sleep. So asyncio.sleep is very similar to time.sleep in the core that you're probably familiar with Python. What that does is it pauses execution until delay seconds have happened. So if delay was 5, it would pause execution for 5 seconds. Now, time.sleep normally blocks, but we don't want it to block, because if it blocks, nothing can happen. We're not reading from the network, we're not updating the game, we're not accepting user input. That's bad. But the other thing that asyncio.sleep does that's different is, first, it doesn't block. Instead, it allows you to pause your current function for that amount of time and let other things happen, and then after the amount of time has elapsed, your function will continue. So what we're going to do is we're going to use this for two things. So the base main loop for the server doesn't do anything because all we're doing is responding to network activity. So it's just going to sleep for a second before waking up. And all that is doing is allowing us that if we hit Control C, so we run the server in the terminal and we hit Control C, it's going to stop the server because every second it's going to wake up to see if anything's happened, and it's going to notice that we've given some input, and it's going to shut down the server. That's literally all it's doing. So we call self.switch1, which is the same as calling asyncio.sleep1. But for the client, where we actually have a main loop that's accepting user input and drawing things, we actually need stuff to happen. But we still want the network communication to happen as well. So because we're handling all of our networking in this module, we don't want the client to have to import asyncio, just net. So we define switch on here basically so we don't have to pull an asyncio in the client, just to make sure it's all nice and tidy. In the client though, all we're going to call is switch with delay 0, the default. What that does is it basically tells asyncio if other events are ready, process them, and then as soon as possible, return to my loop. Don't wait for anything. So what that does is it says if there's data that's already come through, it's going to come through and it's going to put in the data received messages that we defined up here. So it's going to let all of that communication happen. But if it's waiting for a new message, or it's currently downloading the message, or something else is happening, it's going to return control right back to our loop immediately so we can continue rendering. So that is what all of this code is doing here. And again, is server false, is client, is not, is server. Basically, if we're one or the other. And then event loop is none, and the event loop is set when the main loop is executed in case you need to call functions against the loop, such as call later or setting up a task or something. Generally, not something you need to do, but it's there because it can make some things simpler, which we may or may not run into. So let's define our handler here. What is the event loop, I think? Yep. By default, allow connection is going to return true because unless you define some other logic, it just accepts it. These methods, we're just passing. So all we're doing is making sure there is a method there. That way nothing blows up. But you have to define it yourself because the definition here doesn't make sense unless you know whether you're the server or the client. So we'll define that elsewhere. So async def switch self delay equals 0. So async and await, these are new in Python with asyncio. I think async and await are 3.6, I believe, and asyncio came in 3.4. They basically are pretty syntax that lets you define coroutines, which are basically pausable functions that you can yield control to other ones, like our loop, like we were just talking about. So an async definition, an async function allows to cede control basically to the loop, and await basically says I'm currently waiting for something. you could do other things while this is going. There's a lot more like specifics to that is like really high level and not like any sort of technically accurate. If you're really interested in coroutines or you're interested in how Asyncio works, I definitely recommend looking it up. It's been very cool for me to read about it myself, but it's far outside the scope of either this video or my expertise to really go deep into it at this point. All right, so async def main loop, self loop. So we're going to pass in the event loop. And then we're going to say while true. So basically, we're going to let this thing run forever unless there's some reason not to. Await self.switch 1, which is just main loop isn't going to do anything by default. So there's a base handler. Now, I've gone ahead and I've added a second type of protocol on top of JSON protocol to make everything else simpler and go faster. All right? So this is called the command protocol. So the command protocol inherits from JSON protocol, so all the work we already did in the other one is here. But what it does is it assumes that each of the JSON messages contains a key named CMD or command. And what it does is it maps those commands to functions on the handler. Okay? So as you can see on our handler right here, we have functions like handle connection made, handle connection lost, handle message. So if a function on the handler is handle underscore, it means it's intended to be used by the protocol for raw activities. But what command protocol does is it allows us to have def cmd hello world, for instance. So we could define, what we want to do is basically be able to say hello world. And what will happen is if there's any functions or any methods on the class that start with cmd underscore, then there, using the command protocol, those are allowed to be called across the network, basically. Basically, those are handlers for specific commands. And so, whereas these are handles for specific events, which are hard-coded to the protocol, commands are not hard-coded. They're hard-coded in the handler, but your client, the connection, you may receive a command, any command. There's no specific set number of commands you can receive. You simply can only handle the ones that you've defined. So that may be a little bit too amorphous before we get into actually seeing how it works, but let's show you what we need to do to make that happen, and then we'll look at what that ends up looking like, all right? So the command protocol we inherit from JSON protocol, and we don't define a new initialization function because the one that we used before works perfectly fine. What we do is we change 3 functions, and we add a new function, okay? So the functions we change are data received, and the way that data received changes is that all of it looks the same. We have a buffer where we put the decoded data, we parse the buffer into messages, we go through each message, but instead of calling handler.handleMessage for each message, instead we process each message. All right? So when we process each message, what ends up happening is, well, we'll get to that, I guess. I don't want to get ahead of myself. I'm sorry. All right. So we change that so that we do some extra processing of the message before it ever goes to the handler. That's what data received is changed to do. Reject connection is changed to call self.command rejected. So instead of sending, okay, let me leave this here. So instead of sending this byte string JSON with message rejected, instead it's just going to send a command rejected. And so that's going to call the new function we create, which is command. What command does is it takes a name of a command. So you define what the name of the command is. So in this case, rejected. And then it takes any args and any keyword args. So that's what star args and star kwargs does. It lets you say, so what that lets you do is you could say self.command foo. So we call the foo command and we say bar and we say say equals spam, for instance. And that's going to put bar into the list of args, and it's going to put say spam into the dict of quargs. Okay? And then, so basically all it's doing is creating a dictionary, and then it's calling the send message that's defined in JSON protocol, which is going to wrap that up into a JSON message and send that over. All right? So when we reject a connection, we're going to send a command now, which is just means we're going to send command rejected with some args and keyword args instead of sending message rejected. Process message. All right, so here's the real meat of what changes. Now, it looks like a lot of crazy magic, but it is relatively straightforward once we get into it. So we get a message, and we check if there is not the command in the message. So if this message does not contain a command, then we're going to tell the handler, hey, I don't know what this is. So we're going to call self.handler.handle non-command with self, so our connection again, and the message. I believe. I was like, oh, wait a second. When we called handle message before, we weren't passing our connection. That will be a problem. So we fixed that right there. We just got a bug. Yeah, okay. So we're going to send ourself, and we're going to send the message, and we're going to say, handler, we don't know what message this is. Or we don't know what command this is. That doesn't look like a command. So this is something else, right? So the handler for this command protocol is not going to implement handle message because we're never going to call that. Instead, it's expecting all of the communication to be in the form of commands. So if we get something that isn't a command, or we want to define, or we want to allow commands and something else, then that would be how you use handle non-command. Then we define the function name. So the function name is, again, we're using an F string. So we're saying the function starts with command and ends with the command name. So when you call command with name, it gets passed, it sets as the command value of the dictionary. So whatever the name of the command is actually what goes here. So if we say command foo, then, like before, then func name will equal command foo. Okay? So that's what this is building out. Then we're grabbing the args off of the message and the keyword args. And we're saying, okay, if we don't have the attribute of this func name, so what we're saying is for our handler, if our handler has not defined command foo, and we send a command named foo, then it's an unknown command. So the handler will has a handle for that as well. So handle unknown command takes a message, takes the name of the command, and then takes whatever args and keyword args it would take. Okay? So what that's saying is, if you've defined command foo, but you hit command bar and you've not defined command bar, instead you're going to get handle unknown command bar. But foo will work. Okay? Finally, at this point, we know that we understand that we've defined this command in the handler. It knows how to handle it. We're going to get the function with that name. So in this case, it's going to be handler.command foo or cmd foo. Now, here is a slight split, and this is just a convenience. We check if the handler is server. If the handler is server, we execute the function with our self, so the connection first, then with all of the args and keyword args. Because the server is handling multiple connections, every time it gets any sort of network traffic, it needs to know what connection generated that traffic so that it knows how to respond to it. However, if it is not the server, so if it's a client, the client is only ever connected to a server. It doesn't have connections of its own, or it doesn't have clients of its own that it has to manage. So because of that, we can just imply that the connection was the server connection, and we're not passing self through. This just makes defining the handlers and the client look a little bit cleaner, but you can totally send self through all of the time and just define your things to handle it that way. If you want to connect to multiple servers, for instance, or something, you could do that. All right. So again, lots of stuff here. Kind of glossed over it relatively quickly because I want to get through this so we get to the meat of making the game as quickly as we can, because we're already at 1 hour and 14 minutes. So we're just going to go ahead and we're going to implement this. And actually, for the sake of speed, I'm going to copy this over and paste it, because at this point, we're going to run out of time for actually getting to the fun part if we keep going on this. But feel free and pause and look at this, or look at the source code, which will be shared in the video, in the description of the video, as always. So let's just define our command. Okay. Now we need to get a protocol, or a handler for that command, or for that protocol, which is simply this. So this is the same as the normal JSON handler for the JSON protocol. Actually, you know what? We'll name this the JSON handler because it's for that. And it's going to take the JSON handler. And literally all this implements are 2 new functions, which is the non-command and the unknown command. Pretty simple, right? That's just in case we get something that doesn't look like a command, or is a command that we don't have a mapped function for. Now, almost done with the netcode. We have a protocol factory. So a factory, in this case, is something that when called creates something else. That's what a function factory is, or in this case, an object factory. What this is doing is we are defining the factory with the type of protocol we care about, the handler instance we care about, and any args or keyword args we care about. Okay? Then we define the call function. And the call function returns self.protocol class. And that protocol class is initialized with the handler and any args or keyword args. Okay? These could be excluded for now because none of the protocols that we've defined actually take anything except handler. Right? So you don't need all of these. That's purely if you want to implement your own protocol that you want to parameterize differently. Okay? The alternative to this is you could have a function. You could say def factory return. So let's say you have a command protocol and then you define the handler someplace else. You could do it like this as well. All right? And if you do it like this, what's going to happen is you have to define your factory and pass the factory through to different places, because you can't. So what you can do with this one is you can create the factory with the parameters, and then you just call it and it remembers those. With this one, you can't parameterize it. You have to encode it as part of the factory itself, what the handler is outside of it, and it has to be in the scope. And it's just not as clean, in my opinion. So all call does is lets you call the factory. So you can do like A equals protocol factory, command protocol handler. And then you can call A afterwards. Even though it's an instance of an object, you can call it as if it's a function. That's what this is doing. So we're going to copy that over. Okay. Now last but not least, we have a function called run handler. All right. Run handler is going to take an instance of a handler. It's going to take a protocol class, so a definition of a protocol. So by default, it's using command protocol, but you could pass it JSON protocol or whatever you wanted if you wanted to create a different one. It's taking a host. So in this case, we're going to be running against localhost on port 779. So we're going to serve on localhost, or we're going to connect on localhost. If you wanted to host this on a different server, though, you would host it on the that local address, but then your client would have to know the remote address to connect. Okay? Loop equals asyncio to get event loop. What this is doing is it's basically saying, well, it's doing exactly what it sounds like. It's using the asyncio library and it's getting the current event loop. What that lets us do is lets us use call into that loop and run the loop and schedule things against it. Okay? So factory is protocol factory with protocol and handler. So this is that factory class that we created. My apologies. Something flew in my mouth. So we're going to instantiate our protocol factory using the handler that's passed in and the type of protocol. This is important because Async.io's create server and create function classes expect you to give them a factory. So that means you can either use a function, like I was saying, that returns a protocol instance, or you can just pass it a protocol if you don't have any parameters. But we do have a parameter because the protocol needs to know about the handler in order to communicate with it. So that is why we're doing it this way. All right. So we check if the handler is a server. If it is a server, we call loop.createServer. So the event loop, we're telling it to create a server with our factory on this host and this port. So it's going to create a server with our protocol, with that protocol attached to our handler, and we're calling loop.runUntilComplete. What that's going to do is basically say, create server takes some time to know whether or not it succeeds or fails. So we're going to wait until it succeeds or fails before we continue. If it is not a server, we're going to run until complete, but instead of creating a server, we're just going to create a connection. So literally, the only difference here is create server versus create connection. However, handler is server or handler is client is what the handler is set to, and that will handle whether or not we're listening on the port for clients or we're connecting to a server. And again, we're going to run this until the connection either succeeds or errors. Once our connection has been made, what we are going to do is we're going to call loop.runUntilComplete handler.mainLoop and pass it the loop. So again, if we look at our handler class, main loop takes an event loop. That is this asyncio.getEvent loop. We're running until it's complete. So what we're basically saying is this is going to keep doing while true until something happens to interrupt it. And all it's doing is ceding control to something else. So by default, and if you're on the server, that's what you want it to do. If a client connects or disconnects, everything's fine, right? If the server loses its connection, you might have an issue right now. I don't really know. That'd be something to look into as a research project. What happens if the server stops being able to serve? But most likely it's going to generate an error that's going to bubble up and break everything, which is what you want it to do because you want it to stop so you can see what happened. But what this is going to do is basically just run our main loop, pass it the loop, and it's going to run until complete. And in this case, it's going to run forever. However, if you hit Control-C, so if you're running this in the terminal, like we were... 11. Didn't mean to do that. So if you call Python server.py, it's just running. It's sitting there, you see, it's just not doing anything. If you hit Control-C, it's just going to quietly break. So that's what this try except keyboard interrupt pass is doing. If it's a keyboard interrupt, it's going to interrupt the main loop, but we're not going to actually throw an error. If it's any other error, it's not going to be caught here, so it's still going to bubble up. So you'll see what's going on. So we'll pull this over into our netcode, and that's done. And basically what you have here, once you've gotten to this point, is you actually have a very simple, basic Async.io networking library that uses JSON as the transportation language, if you will, the data language to communicate. Now, the cool thing with that is that lets us start doing the fun game parts. All right? So, first we're going to create our server. Okay? Server is going to handle all of the logic in our game. A client, a game client, so a player, they're going to make commands and stuff, but that client is simply going to send those commands to the server and let the server actually figure out what to do with them. That way, it keeps in sync between player 1 and player 2, and there's no risk of cheating because the server won't allow it. So in the server, am I using async? I'm not. So in the server, we're going to import random. Why are we importing random? Well, when you play a game, it's going to end. And if you want to play another game, you want sides to change, right? You don't always want to play as X or always play as O. So it's going to determine for you what it is. Now from the library, we're going to import the grid from lib, import grid, net. So the cool thing with the way that we defined our grid before is this going to work on both the server and the client side. So we don't have to have a specialized version of it for either one. So we're going to pull in the grid in the net. We're going to create a class player. The player simply tracks what connection that player is connected on, what their wins and losses are, and what their current side is. Okay, very simple. We're just going to set it to side equals X to start, even because what's going to happen is once the game actually starts, the sides will be determined, so it doesn't really matter. We're just going to set it to a valid value to start. Okay? Next, we're going to have a game object. So this game class, all it does is track whose turn it is and keep track of the game grid, so what values we have. It then defines a helper function which lets you make a play on the X and Y. So whoever's turn it is currently, you make a play on X and Y. It's going to take whatever turn we have and update the grid on that position. Now remember, grid.update returns true if it successfully updates and false if it fails. So basically you're trying to update something that doesn't exist or is already set to something else, which was set here, right? So we do an update. If it's not free, we return false. Otherwise, we return true. Okay? So if it's successfully changed, or if we successfully made the play and we updated the grid, we're going to change the turn. So we're using a ternary operator here, and we're saying self.turn equals O if our turn equals X, else X. What this is saying is, if the turn is X right now, set the turn to O. Otherwise, or if it is O, set the turn to X. It basically is just swapping what turn it is, right? And it's returning true. So this is following on with the way that grid is returning. So make play will return true if it succeeds, or false if it was an illegal move, and nothing will change, and turn will not change. Game over is simply a helper function that returns grid.gameover. And grid.gameover, as we defined, basically returns X or O if one of them won, or tie if there are no free cells left and nobody won. Otherwise, it will return false, indicating the game is still running. So we're just going to copy that and pull that over here into the server. Now, we have our actual server handler, okay? This is the cool part. So at this point, now we're actually defining some logic for our game instead of just our networking backend. Remember when I was saying that whenever you're doing networking, it adds a lot of complexity to the game? Well, you have to do a lot of this setup in the backend. That way you can build the game up. You could totally make this game and just do the client to start and then add networking, but that's going to be way harder. The reason it's going to be harder is unless you're simply using that as a reference point for the functionality of how the game should be played, you're going to have to rewrite most everything to make it work as a networked game. If you're making a game and you want it to be multiplayer, the best rule of thumb anyone has ever given me, and I will pass on to you, design it to be multiplayer from the beginning. It will save you time and headache. The downside of that is you do have to set up all your netcode and stuff at the beginning, right? So it takes longer to actually build the game. We could have been done with Tic-Tac-Toe at 30 minutes, an hour ago, if we had just done it the simple way, right? But the multiplayer part of it added an hour and a half probably, right? So if it's about 30 minutes to make Tic-Tac-Toe, it was an hour and 30 minutes to make the network code, there you go. It takes 4 times longer to make the networked version. Obviously, that doesn't necessarily always, like, obviously, that if it was a more difficult game, we already have some netcode, so we could probably use Pong with the same netcode or something. So that's kind of just a silly thing to say. But you do have that startup time, and you have considerations you have to take into account when you're designing the game. All right? So we're going to continue here. We're at the hour-and-a-half mark. I'm really going to try and keep this under 2 hours, but I have a feeling we might go over today. My apologies if we do, but we're going to try. All right? So first things first, we're going to make our server be a subclass of that command handler we created in the network code. We're going to initialize we're going to call the command handler initialize with isServer equals true. So what we're basically saying is, hey, we know this is a server handler, so we don't need to send that in as a parameter. Just send that as the parameter default to the initialize and let that handle itself. We don't need to actually set that anywhere else. Okay? Self.players equals a list. This is so we can track what players are currently connected and what their connections are, and we can interact with them. We also have self.playerById equals a dict. What this is so that we can say whatever the ID of the connection. So up here, when we have the protocol and we have a handler, each instance of the protocol and thus protocol handler around the transport has a unique ID. And that allows us is every time a connection happens, we get the connection. That's part of what the server gets, right? That's why it was so important that we always let the server know what the connection is when it gets sent or when something happens, because we can look up the ID of that connection. So what this is doing is we're mapping the ID of the connection to our player object it represents so we can look it up. Then we also do self.game equals none. This is to track our game object, but since there's no game happening, it doesn't have any value yet. Okay? Now we're going to define first our handler methods. So I broke this out. So up at the top, we have our handler methods. So these are methods that that are called directly by the handler for actions that are not commands. Okay? So in this case, we have allow connection. So we're only allowing 2 connections. So if we're less than 2, allow the connection. Otherwise, we're not going to allow because there's only 2 players. I do have a to-do in here, so this is a perfect place for you to do your own change and to allow more connections. But instead of having those connections be players, have those connections be spectators that cannot play. And you would have the UI tell you that you're spectating, and you would never see it being your turn. So just the 2 players will get updated, right? But the spectators can see everything that's happening. That would be a cool thing to do, but for now we're only allowing 2 players. If another one comes in, it gets rejected, okay? Second, define handle connection made. So when a player comes in, we're going to just print it. That way we have something in the server console to let us know that it's working. We're going to tell all of the other players. So if we have another player already, so when we say all, in this case it's other, if we have another player, we're going to let them know that another player just joined. Then this new connection, we're going to send a command. We're going to send a welcome command, and we're going to tell them how many other players there are. In this case, since we're only allowing 2 players, that's either going to be 0 or 1. Okay? Then we're going to create a player object that wraps around the connection that we defined above. We're going to append that to our list of players, and then we're going to also store the connection ID, or we're going to store the player mapped to the connection ID here. That way we can look it up like we were talking about. Also, if the number of players is now 2, we're going to schedule a new game. Which is really cool. So what we're saying is as soon as we reach 2 players, we're going to start a game. And start game is going to say, okay, in 5 seconds, for instance, a game is going to start. Now, again, if you change this so you allow more players as spectators, you're going to have to change the logic here to check if you're already playing a game when you get a connection. And you basically don't create a player, create a spectator object or something, and handle that differently, but send to all should also send to the spectators. So there's a lot of things you're going to have to pay attention to, but it'd be a cool problem for you to fix, okay? But yeah, this is another area, this right here, you're going to have to pay attention to if you try and conquer that challenge. Handle connection lost is saying, okay, we lost this connection. That player goes away. We're calling self.getPlayer connection. What this is going to do is go to that player by ID, pull the player based on the connection ID, and return it to you. This is just a helper function to do that so you don't have to go to player by ID. But I don't know that anything's actually calling... Actually, other things are calling it. So that is a helpful helper. So we're getting that. That is defined right here. It just returns self.player by ID, connection.id. We're just looking at the player by the ID. We're removing that player. We're deleting that ID map. And then any players left, if there are any, we're telling them the other player left, basically. Okay? We're also wrapping in non-command. So if we get a non-command from the client, then we're just like, I don't know what happened. So we're sending the client invalid command to let them know that they screwed up. And then we're closing the connection saying, you did something wrong. Go away. Try again. Okay. So we're defining our helper functions here. So the send command to all that we've been using everywhere, that takes the name of a command. It takes the number of args and keyword args. And then it just goes for player and self.player. So loop over our players. Each player use its connection and send the command with the same arguments, basically. Get player, we already talked about here. Schedule start game, we were talking about before. We're going to send a command to all of the players, so both the players in this case, the two players, telling them next game soon and how long they should be waiting. So in this case, we're going to have the game start 5 seconds after all the players are in. So they have a little bit of time. This is also if the game ends, how long before the next game starts, right? So because of that, we're going to say, we're giving a little bit of time for people to observe their final of their game. And then we have start game. So this is where we start getting interesting, right? Okay. Start game, make sure that we have players because maybe we scheduled the game to start and then a player left before it started. So we're just going to be like, well, oops, didn't work. Sorry, go away. Game doesn't start. Otherwise, we started the game. So we set our game to a new instance of game up here, right? And we are going to decide who is player X and who's player O. So player.x equals random.choice self.players. Random.choice takes a list of values and randomly picks one of those values. So this could be player 1 or it could be player 2. It's going to change each time. Well, some of the time. Since there's only 2, it's, you might be twice in a row, 3 times in a row. Who knows? But player X is going to be the player. Then we're going to loop over each of our players and check if that player is the player X. So if that's the player that was chosen, its side is X. And we're going to tell it start the game. The turn is X. So when we initialize the game, it sets turn to X. So X always goes first. And we're telling the player that the turn is X, basically, or whatever the game turn is. Maybe you want to have logic in there that makes the who goes first be random. You could totally do that. And then you can just here, when you initialize, you could simply say random.choice XO, right? And that's all you'd have to change. So go for that. That'd be cool. We're also telling it that its side, that player's side is X. Otherwise, if the player is not the X player, their side is O, and we're letting them know that. Okay? So that's it. We're just setting up the game holder so that we know that we have a game going, and we're telling each player what side they have, and that the game has started, and whose turn it is. Now is the cool stuff. So once that game has started, players can make plays, right? You can move around with your keyboard to select a cell and hit enter to try and put your marker there. So that if you hit enter and you send that to the server, you're going to send, hey, this connection wants to make a play at X and Y. So maybe it's X0, Y0. So if not game, then we're going to tell it, hey, dude, don't, we're not playing yet. Calm down, slow down, right? Which is not going to happen in our client because our client checks if the game is running. Our game client is going to check if the game is running before it sends the command. But, maybe someone's trying to do something stupid. Who knows? All right, we're going to grab our player. So player equals self.get player connection. Again, that looks up the player using the connection ID. We check if the player side is the current game turn. So if player is X and the turn is X, then it's their turn. So if not player side equals game turn, so if it's X and game turn is O, or player is O and the game turn is X, then it's not your turn. We're going to scold that player and say it's not your turn, and we're going to return out of this. We're basically going to just say, okay, this command failed, right? Now, we're going to say, okay, if we get to this point, it's that player's turn. We're in a game. Okay, let's try to make that play. So success equals self.game.makePlay, XY. Now remember, this function is going to call the grid makePlay function, and that function is going to return true if it was a successful function and false if it was not. So if not success, connection.command illegal play. We're just going to be like, you can't do that. That doesn't work. I'm sorry. And we're going to, again, cancel out the function, the command. However, at this point, if that command succeeded, then that means the turn has changed. That means that that cell has been updated with that player's marker, and it's now the next player's turn. So we're going to send a command to each player called update game, and we're going to send the current map, the current game grid. So the cells of the grid are those, lists of strings, right? So you have 3 strings inside of a list, and you have 3 of those. So that is our grid. What we're going to do is say, okay, we want all of the players to make sure they're on the same page, so we're just going to send the whole grid. Now, alternatively, what you could do is simply tell each player which move happened, and they can update their own grid. That's perfectly valid as well. This is just simpler to keep everything in sync for the purpose of the tutorial, I feel. We're also going to send whose turn it is now, which basically is just saying, well, the client should know whose turn it is if the game updated, right? But we're just going to tell them to make sure that everything is in sync. Then what we're going to say is, oh wait, there might have been a winner based on that move. So winner equals self.game.game over. It's going to check whether it's a game over status. If not winner, then the game is still going. We now cancel out the command. Everything's good. We're done. Otherwise, let's let the players know who won or tied. So for player in self.players, we say tied is false and won is false. So basically, by default, it's false. Now, if the winner is a tie, then the player ties increases by 1, so their results increase. And tied equals true, so we can send through that it was the tie, not a win. If the player's side equals the winner, that means they won. So we increase their wins and we say, hey, you won. Otherwise, player.losses increases by 1, and it was neither a tie nor a 1, which means you lost. So then we're going to send to that player the game over command. We're going to say, you won, true or false. You tied, true or false. Here are your current wins, current losses, current ties. Make that big so everyone can see. Then, after both players have been told that the game is over, we're going to schedule a new game, which is going to tell them, hey, in 5 seconds we have a new game. Enjoy the beauty of that previous game while you can. And then at the bottom down here, we have a main function, because I just always like putting a main function in files that are executable. Generally, I put if double under name equals double under main, then execute main. But in this case, server's always going to be executable, so whatever. We create a server, so we basically initialize our handler up here. Our server is a handler. And we called net.runHandler, and since our server is a handler, we pass it through. So remember, in the run handler code that we created, it takes a handler. The protocol by default is command protocol, which is what we want, so we're not changing that. And then we're not changing the host or the port. So basically what this is going to do is just run the server. Cool, huh? Now, you could do some cool stuff where you make the handler, you just call handler.run or something, and then it actually does the initialization, which would actually be pretty cool and would make things, I think, a little bit cleaner in some sense. but that would also make the handler have to have all of that stuff in it, and I don't know. I didn't go that route. You can if you want. Diverge all you want. This is just a starting ground, like we said. All right, 15 minutes left. That's the server. So again, 15 minutes left. So we're just going to copy the rest of the server because I know it works, and we just talked through line by line, and I don't have the time to re-implement it all if we want to get through this. Sorry. I really wanted to, but this is going slower than I expected. All right, next thing, we have our game. Here is our game client. This is where we actually get to play and do stuff, right? All right, so this is going to use everything we built so far except the UI. UI we haven't built yet, but we will get to that. There's just a couple functions it calls into the UI, so we don't have to actually specifically figure that out yet. But we will get to that last because that is the part that's kind of the most standard to everything else we've done, so we can probably breeze over that. And if you need a refresher on how that stuff works, you can look at the older videos, okay? So we define a game object very similar to the servers, but with some slightly different things because we have some status tracking in here, which is we track whose turn it is, so we track what our side it is, whose turn it is, whether we are starting a game, so basically whether we're currently between games, right? Whether we're currently in a game, our current wins, losses, and ties, and the current game grid, which is, again, the grid to grid. And then we give a helper, my turn, which basically says it is my turn if we're playing and my side equals the current turn. Pretty simple. That just is a helper way for us to track, whether to display that you can move, okay? Class game client is the net.command handler. So again, this is just like the server. We create a handler for our game, for our client. In this case, it's the game client handler. So when this one initializes, we're going to pass the screen, right? So with Pygame, you create a screen, which is basically the display that you get a draw to that will create your window. So we're going to pass it the screen. We're going to initialize the handler with isServer false. That way we know it's a client. And we're going to say self.game equals game. So for this one, so if you notice on the server, every time we start a game, we reinitialize the game object. But with the client, we're just going to have a single game, and it's just going to track over the life of it and reset. Self.running equals true. This is whether our game client is running. So this is an easy way for the UI to say, hey, we hit escape or something. We should shut down the game loop. This is how we track that. Have opponent tracks whether or not another player is connected to the server or not. That way we know whether we're waiting for them or if we're ready to play the game. UI. So again, we haven't initialized that, but we just define it by passing our self to it, so it has access to all of the current game state, and we pass that screen from the Pygame initialization. We create a clock for ourselves. That way we can determine how fast we want the FPS to be, and we can set our target FPS to 60. Okay? Fairly straightforward. Here are our connection handler methods. Very much like the server, we're going to have the handler methods together, and then we'll have helper functions, and then we'll have those commands as a separate thing. That way they're each in their own place. So we're going to define our main loop. Main loop takes the event loop, and we're going to store that event loop as always. We're going to change our while loop, though. So instead of saying while true, we're going to say while self.running. That way if something says self.running false, next time the loop runs, it will realize, hey, we're supposed to be ending. Stop the loop, clean up everything, we're done. It's a very clean way of handling that, so that you don't have to, do an error to crash out the game, and then, you might have the window frozen and stuff like that. Self.clock.tick. So this is using Python's tick functionality from their clock. What that does is it tracks what the previous few FPSs, basically how long it took between the previous calls to tick, and what the target FPS you want is, and it tries to limit how fast the server is running, or the game loop is running, to match that. So basically with a game like this, right, it's so simple, you could probably have 1,000 FPS, but then you'd be using up a lot of CPU, and it'd be running really, really hard as if you were playing a really intensive game, even though you don't need to. So this is going to limit and say, okay, we don't need any faster than 60 FPS. You probably don't need faster than 30 for this. Hell, you probably don't need faster than 10 for this. But we're going to target 60 just because that's a normal modern game FPS. And you certainly don't need like 144 hertz for this. So 60 is fine. But you can set that to whatever you want. Now, do note there's a to-do in here, which is with Asyncio, clock.tick doesn't actually integrate with Asyncio. It's going to actually block. So let's say, 60 frames per second basically means each frame takes like 12-ish milliseconds, I think, something like that. Quick math. So 1,000 milliseconds in a second divided by 60 FPS, 16.6. So if your frame time, so what clock.tick is going to say is we're going to make each cycle of the loop take 16.666 milliseconds. Okay? So what that means is if it only took 1 millisecond to do the last run of the loop, it's going to sleep for 15 milliseconds. Okay? For this game, that really doesn't matter. But in general, to be more asyncy, as I put here, it would be far better to track yourself what the previous ticks were, like how long they took, and figure out how long you should sleep, and use the self.switch with that amount of time. So basically calculate for yourself how long you need to delay to hit the FPS you want to maintain. So at 60 FPS, delay so that you take 16.6 milliseconds basically for each of these loops. If you do that, that will let this pause that full time and not block. So any network I/O can happen in that time a lot more cleanly. And other things can be happening. It just won't be checking the UI or updating the render, which is really what you're going after with it. So for this, it really doesn't matter. But if you have a bigger game or a game that, maybe you're playing Pong and you're setting a lot of different updates, you want to get those updates as soon as you can so you delay or you minimize the impact of your ping. Because if your ping is 100 milliseconds, but you're sleeping for 16, it's going to kind of basically inflate your ping to 116, basically. So we're going to sleep. We're going to basically make sure that we're hitting our target FPS, or we're not going over it, I should say. We're going to call the UI update. So we're going to tell our UI to check if there's been any keyboard presses and do stuff. And then we're going to render our UI. And then we're going to await the self.switch, which lets everything go back to the Asyncio library. And it's going to use its event loop to check if there's been any network activity. Handle unknown command. This should be the first handle that you instantiate for the game client. This basically is just going to print out the name of a command if it doesn't know what it is. That way, as you're doing development, this was the first thing I made. So as soon as it connects to the server and the server sends it something, it's like unknown command, blah 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 blah. So I know what the next thing is that I need to implement, and it just makes it so that we know if the server's sending stuff that we don't know about. Define handle connection made connection. We only have one connection like we were talking about, so we're just going to remember what our connection is. We don't need to map it to players or do anything like that like the server is. We just know that we have it. Handle connection lost. If we get disconnected, we're just going to shut down our loop because that's our whole game. Pretty simple. Helper functions. We have a function to make a play. So what this does is it checks if it's our turn, and it checks if the grid is free where we're trying to make the move. If both of those things are true, we're going to send the command to the server and say we want to make the play at the X and Y. So we're going to check ourselves whether it's our own turn and whether it's a free grid. That way it minimizes the likelihood that the server is going to tell us that it's not our turn or it was an illegal play. So we're being nice that way. You could totally just call self.connection.command and it would just send back those other commands and say, no, it's not your turn. But we're doing it this way because it's, in general, if you can do a check on the client side, I feel like you want to, because you're not using up that network resource, that bandwidth going back and forth, and you're not waiting on the server. It, again, for Tic-Tac-Toe, it really doesn't matter, but I think this is, in general, is the better way of handling it. So we're doing it here. Now, we're going to handle all those commands that the server can send us. So we know, so basically we know what's going on in the game. Command welcome, this is sent when we join the server. It's letting us know if there are other players. So if there are other players, so if it's more than 0 other players, we know we have our opponent. So we can store that, so we know we're not waiting for another player. Otherwise, if we get the player join command, that means we were player 1, right? So there wasn't another player here. And we know that there now is another player, so now we know we have an opponent, and we're not waiting for an opponent. If player left, again, that means that our opponent left. Now we no longer have an opponent. Next game soon means, hey, we have a game starting. So game starting equals true. Game playing equals false. So there's a to-do in here. If you saw when we ran the game, the prep game that I did, it doesn't let you know how long you have. It just says starting ... and then it goes into the game. This would be a good place for you to change that to track how many seconds until it starts. So it counts you down. 5, 4, 3, 2, 1, playing. That would be a great place to add on to this to do something cool. And then, once the game starts, we're going to get the start game command. It's going to tell us whose turn it is and whose side it is. So we're going to say game starting false, game playing true. We're going to set whose turn it is. We're going to set what side we have, and we're going to reset our grid. So if you remember back, grid.reset, all that does is create a new empty grid, basically. Whoops. Oh, come on. Where was I? Okay. And this is going really quick now because we've done all of this baseline work. All of the rest of this kind of should just flow and sort of start to make sense. Hopefully, anyway. Update game. So this is coming from the server after someone makes a play. So they're going to give us new cells, which is basically the new grid layout with where everyone's played and whose turn it is now. So we just update the grid. We say, okay, set our cells to that. Also, change the turn to whoever's turn it is now. Game over takes whether we won, whether we tied, how many wins we have, how many losses, how many ties. We simply update our game with those wins, losses, and ties. And here's another good place to do UI. I'm losing my voice. I'm sorry. I'm trying to get through this. It looks like we're not really going to hit the 2-hour mark, so I'm going to slow down a little bit. Stop talking quite so fast, because we're not going to hit 2 hours, but I'm still going to try and get through it as quickly as we can. So this is another good place for you to add on. For now, if you won, it simply prints out in the console you won or you tied. Otherwise, if you didn't win, you didn't tie, you lost. Right now, it doesn't really do anything. It just simply tallies that you lost. It doesn't show you anything. It doesn't give you any feedback. Our main function for the client is very similar to the server, except we're initializing Pygame. We're creating a display. We're creating our client handler and passing it the screen. And then we're calling net.runHandler with our client. So this is going to block until it finishes running, right? So as soon as this is done, it's going to pass over here. With Pygame.quit is going to close our screen. So it goes away and everything is nice and tidied up. And that is our game client. Very simple. This is the server and the client connecting to it using the network. Once you have that command helper, it really is easy to just handle any command going back and forth. If you'll notice, there's quite a few commands that we didn't implement from the server because we're unlikely to run into them, such as the not in game, not your turn, illegal play. But you could implement those and let the server handle those instead of doing all the checks in the client. Totally up to you. So we have one last piece. One last piece to tie everything together. So that last piece is the UI. So the UI is a user interface. And all that is doing is it's taking the game client and it's taking current game status and displaying that to the screen and checking for user input. And that's really all it's doing. All right? But there's quite a few lines of codes here just for the simplicity's sake. So we create two fonts. We create a bigger one and a smaller font with none. So that means we're just using the system default font. Hover X, hover Y. So this is actually. You know what? Let's change this to grid hover X and hover Y. In case you're curious, I'm using some of the shortcuts that you have in Sublime to mass edit and replace things. So if I press Control D on this, and then I press Control D again, it copies all of the instances of it, and then I can edit all of those together, or I can move to the beginning and change them. So grid hover X, grid hover Y. So this is which grid are we looking at? So if it starts in the top left and we arrow down, we're looking at the left side middle cell, right? So this is just tracking which cell we're looking at. Grid width and grid height. This is for rendering purposes. How big do we want to render the grid? So our screen is 640 by 480, right? So 300 by 300 means not quite half of the screen is going to be the grid. That way we have room for the UI elements around it. We also have grid position X and Y. So this is the top left of where the grid is. So at this position, this is where the topmost part is. Everything else for the grid is going to be like, in relation to this. We call self.calculate grid positions, which we'll get to in a minute. That's right down here. And then we just define a bunch of colors. So background color. So let's just call that background color. That way it's clear. So the background color, line color. So this is the grid lines. The color for the X and the O. So these are all just white. You can change those to be pretty. Go for it. Hover color is the color of the cell we're hovering. So we're making that green. And if we're hovering over, so hover filled color is if we're hovering over a cell that already has a value. So we're going to make it red so you know where you're looking at. Calculate grid positions, called here. What this does is it's actually calculating points of interest for the grid. So our grid is actually just a number of points. And the intersection of those points defines where our lines are and our cells are. So our leftmost position is that grid position X. The end of the first cell, so the first wall, the first vertical wall, is grid width divided by 3 plus our position X. So we take our position X plot and then we add one cell space. So there's 3 cells, so that's grid width divided by 3. Then we take our grid position plus 2 cell positions is the second wall. And then the fourth one here is our full grid width plus our position. So this is just what is the right boundaries. There's no wall there per se, right? There's just the edge of the horizontal lines. So the grid Y positions are the exact same except going in the Y axis. So grid position Y first. Then we have a grid position Y plus a cell. So actually, you know what? Let's just do this so it's clear. Cell width equals self.grid width divided by 3. And that's an int. Because, and this is a Python 3 versus Python 2 thing. In Python 2, if both of these are ints and you divide by 3, it's going to do I believe a floor or a ceiling. So it's basically going to return an int. So if you have like 1 divided by 2, it's not going to give you 0.5. It's going to give you, I believe, 1. But I can't remember. It's 1 or 0. In this case, it's actually going to give you a floating point number. However, we only want an integer. We don't really care how it's rounding because it's close enough for us. So we're just converting that into an int. So cell width. So cell width times 2. There we go. So this makes it very clear what we're doing here. So we're saying a cell. So basically it's our leftmost position plus 1 cell height. Leftmost position plus 2 cell heights. Leftmost position plus the full grid height. So these are points of interest which are going to be useful for drawing our grid. Move X, so this is for our UI. So this is moving which cell we're highlighting. So in the X direction, we're going to move +1 or -1. So if we return 1, we're going to go self.grid hover X plus equals 1. Otherwise, if it's -1, we go 1 to the left, so to the right, to the left, etc. But then we're going to bind our cell positions. So we're saying max self.grid hover X 0. So what this is saying is if our grid, if we're trying to hover over a cell less than 0, that means we're off the map, so we reset it to 0. So if you keep pressing left, you're going to stay on that 0 cell. We're also taking the min of our hover X and 2. So again, if we try and go too far to the right and our grid hover X becomes 3, it's going to put it back to 2 because 3 would be invalid. Moving Y is the exact same as moving X, except you're in the Y axis. Update. So the update function here, all it's doing is getting the events. So this would be the user input events, and it's doing stuff with them. So if the event.type equals quit, so that's analogous. That basically represents hitting the X in the top of your screen. Yeah, you can see that. Okay, cool. So if you hit this, it's going to trigger a quit. So when we create our window, if you hit the X, what we're going to do is we're going to set our client to running as false, and we're going to return. So we're done handling updates. We tell the client it's finished. It quits out. If we have K right, so that would be the right arrow key, then we're going to move 1 to the right. We're going to move 1 in the X direction. If it's the left arrow key, we're going to move -1 in the X direction, so to the left. If it's up, we move -1 in the Y. If it's down, we move 1 in the Y. And if we get return, if we hit escape, it's the same as hitting the quit button. It's also going to stop the loop. Sorry, I missed that one. If we hit return, so that's your enter key. If you hit that, it's going to call self.game client to make play with our hover X and our hover Y. And the game client is going to basically check, is it my turn and is this a valid play? Then send that away. Pretty simple, pretty straightforward what this is doing. It's very similar to the other event loops or the event checks that we've done for the other games in the series. It's just done inside of a function instead of as directly in the loop. There's a to-do here, so you could actually check whether or not it is our turn to not allow it. So if it's not our turn, we're not going to render what cell we're hovering over. So because of that, it sort of makes sense to not allow movement, because right now you could actually move to the right and not see that you're doing it, and then when it's your turn, you're going to see yourself all the way on the right. So that would be an extra, addition you could make. So we're going to do here, so this function draw text, this is a function that is basically used to draw all of the UI text that we have. So if we don't have opponent, so if not, self.game client to have opponent, oops. So if there's no other player, then we know that we're waiting. So we're going to take our small font and we're going to say using, so in red, waiting for other players. So it's kind of a status message. We're going to put that in the top left. So it's going to be 10 pixels in, and we'll make it 10 pixels down. So there's a little bit of padding there. So we create a rect. So text.getRect. So text here is going to return a pygame.image, or actually a surface, pygame.surface. And you can call surface.getRect. So it gets a rectangle representing the shape of the text. And in that rectangle, you can actually set the position with the keyword top left or mid top or top right or what have you. So we're using that for positioning our elements. It's a really simple way to do it if you don't want to have a full-on UI where you're positioning stuff in different places with padding and like CSS and stuff, or style sheets, I should say. And then we're going to draw our text on the screen with Blit. So, I mean, all of this is stuff that's been covered several times before. If you've gotten to this part in the series, you certainly know how to do this. So I'm just going to kind of skip ahead. So if we're starting, we just let the user know that we're starting. We put that in the middle of the screen at the top. If we're playing, we let them know that we're playing. Again, in the middle of the screen at the top. We're going to make this a slightly different color for starting versus playing. Else, we're waiting. So waiting is going to be this color, for instance. So it's slightly different. So the user has some visual feedback. So we're waiting. So basically this section of ifs is basically, are we starting, are we playing, or are we waiting? Then we're going to render, okay, what's our current score? So how many wins do we have? How many losses do we have? How many ties do we have? Each their own little position there with F strings. All of them in white. All of them in white, apparently. I didn't remember that I did that. And then if we're playing, we're actually going to let the user know which side we are. So we're going to say, hey, you are X or O. And X or O is based on self.gameClient.game.side. And we're going to render that in the middle of the screen below the playing sign. Again, pretty straightforward, just lots of little text things for rendering. Next, drawing the grid. So this is kind of fun. So we're going to use pygame.draw.line and pygame.draw.circle. So the lines are going to be used to draw all of the lines of the grid, and then line is also used for drawing the X, and circle is used for drawing, obviously, the O. So our lines, so we define what our lines are for the grid, and this is using the grid X position. So these are those points of interest that we create in calc grid positions. So our first line goes from the grid X position 1, so one cell in. So leftmost, right? One cell in is the right of the first cell. So we're taking the first cell of the X from the origin position of Y, and we take the first cell of X to the final position of Y. So that gives us our first vertical line. Second vertical line is cell 2 in X, again using the beginning and the ending of Y. Now for our horizontal lines, we go from grid X position 0, so the leftmost side, all the way to the first Y height. So the first cell height. And then we take grid position 3, so all the way to the end, the right side of the grid, down to, again, that first Y cell. And then the second horizontal line, again, we're going to go from the left side to the right side, and then we go, not in the camera, and then we're going to go on the second Y cell below it, right? For each of those lines, we're going to call pygame.draw.line, so we're drawing it onto the screen with our line color, and then line 0 is the first two positions, and line 1 is the second two positions for each line. So that's going to draw each of our lines. And then we're going to draw our cell values. For X in range 3, so again, there's 3 cells in the X range, and there's 3 in the Y. So cell left is the grid position, the grid X position that we calculated for that X. So that's the left side. So the left side of the cell that has no wall is the origin position, and then plus 1 cell size is the right side of that cell. So that's X and X plus 1. And then for Y in range 3, we calculate the top and the bottom of that cell the same way as we calculate the left and the right. So then we grab the actual cell from the game grid. So get self.gameclient.game.grid.cells XY. And then we set the thickness. So the thickness of the X or the O is based on this. So how many pixels thick we're drawing. So if the cell is X, if there's an X there, we're going to draw 2 lines. First line starts in the cell left, in the cell top left, and goes to the cell bottom right. And the other line starts in the cell top right and goes to the bottom left. So you get your X. We're using the X color and we're using our thickness. Otherwise, if the cell is O, then we're going to find the center of the cell. So we take cell left plus cell right divided by 2 gives you the center of the cell. So the center X and the center Y. And then the radius is the, so in this case, the cell is the X and the Y are the same height in pixels. But if they are different, generally speaking, the Y would be the shorter one because the pixels are longer. So you would make, so like for instance, our screen is 640 by 480. It looks like it's a square, but there's only 480 pixels in the Y and there's 640 in the X. So this is preferring the cell Y column for determining radius. That way we don't go over it if the X is bigger, if the width is bigger than the height. So we're going to take minus 20. So each of these is padded 10 in. So if it's on the left side, it goes 10 to the right. If it's on the right side, it goes 10 to the left. Or if it's on the bottom, it goes 10 up. If it's on the top, it goes 10 down. So we're going to take 20 off of the radius. So we're putting it in the center and we're taking 20 off. That way we're inside 20. And we're dividing that by 2 because we want the radius. And then we're drawing a circle. So we draw it to the screen with our color. We put it in our center, X and Y position. We give it our radius and our thickness, and that's going to draw the circle at that position. Looks like a lot of code, but in truth, it's one of the simpler things that we're doing here. And it's pretty easy to figure out what's going on. Again, if I'm going too fast or if any of this isn't clear, feel free and let me know. I feel like this is probably stuff that's already been covered a lot more in the other episodes, so I'm kind of glossing over it a little bit. Draw hover, finally, is the last individual thing before we get to the render function. So what this is doing is saying whichever cell we're currently selected, basically whatever cell we have selected, we're going to render that we're hovering over it if it's our turn. So we're going to get the grid positions for the left side of the cell and the right side of the cell on the top and the bottom. And we're actually going to build out a rect. So in the rect, Pygame rect, you can actually give it left and top position. And then you can actually give it the width and height. So cell right minus cell left minus 1, because you want it to be inside the line and not overlapping it. So we take the top left, top right. Actually, you know what? We're going to go +1 here, +1. We're going to go -2 here, because we don't want our highlight to be overlapping at all. Oh wait, no, it already isn't. Sorry, I'm a dummy. Because of the other way it was doing it. Is it? No, it would. Okay, so what this is doing is saying we're going to go 1 pixel to the right of our left side, 1 pixel down from the top side, and 2 pixels up from our height, and 2 pixels up from our width, because basically we're going 1 in here, so you're subtracting 2. Okay, and so we're defining this rect. We're giving a thickness of 3, and then we're checking. So if this cell is free, so we check the game grid. If we check free with our hover X, hover Y, then our color is our hover color. Otherwise, the color is the filled color. It means there's already something there, so we can't actually do anything there. And then we draw the rect on the screen with just to our screen with our color, the rect we created up here, and the thickness we defined there. And then, last but not least, the render call of the UI simply fills the screen with the background color, draws the text, draws the grid, draws what we're hovered on if it's our turn, so that's our turn indicator as well, and then it flips the display. So once you have all of those components, you have Tic-Tac-Toe. So we're going to come in here, and we're going to open 3 terminals. Okay? Again, you could use this in whatever terminal you have, or the Python command prompt, or the Windows command prompt. It works perfectly fine. So this one here is going to run the server. This one's going to run the game. So we got 1 player. Player 1 is sitting here going, okay, we're waiting. I'm waiting for the other player. I haven't done anything yet. Here's our grid. We're going to have another player connect, though. Oh, okay, so other player connects. Neither of them are waiting, so that status goes away. It tells us we're starting. Now the game has started. Player 1 is X. Player 2 is O. Is X's turn, so X is going to make a play. So let's do a tie to start. So X is going to go in the center. O is going to go over here. X is going to go here, because this can't be a winning move for this. O is going to come here, I guess. X will come here. O will come here. X will come here. O will come here. And X will go here. Boom. You tied. You both tied. So we see each player got 1 tie. And it printed out that we tied. And then 5 seconds later, we're now on new playing. So player 1 is still X, player 2 is still O. So this time, let's make X win this time. So X goes here, O goes here. X goes here, O goes here. X goes here, so player 1, it shows you won. Player 2 shows you lost. They both say starting. And now player 1 has 1 win, 0 losses, 1 tie. Player 2 has 0 wins, 1 losses, 1 tie. Pretty simple. All things considered. I do notice that the rect is overlapping on the left side, I think. So we'll fix that real quick here. So we hit escape, which pulls us out of the game. Connection lost takes 2. Hold on a second. We didn't specify the connection lost. So the server is like, no. All right, so let's go to our UI here. Let's see what we got here. So we did +1. Let's see if thickness 1 fixes it. So we're going to run the server here. We'll run client. We'll run each of these 2 here. I guess that's his and that's his. Oops. It's prep that I'm doing it, not here. I think what I might have to do is do like +2 -4 or something, because thickness is 3. So because thickness is 3 at 0.0, it's going to draw 1 to the left and 1 to the right, I think is what it is. So let's just close these guys here. So server's running. Server doesn't need to be restarted because it's already in a position to just accept new guys. And now we're starting here. And then so that's like almost there. Like, so this is just, you know, basically at this point we're done. It's just like playing little things, or like messing with little things to see what we need to do to get it to work. There you go. So that puts the selection criteria like for right inside, so it's not overlapping. And that looks a little bit nicer. But that's just a value you'll have to play with, and that's just getting used to the Pygame.rect and the fact that I haven't touched it in like ages. So there we go. We've got Python. Oh, wow. I noticed on... Hold on a second. Oh, okay. On my preview for OBS, it's anti-aliasing to the point where it's actually like losing the lines here. So hopefully that doesn't happen on YouTube, but if it does, my apologies. You can rest assured the lines are there. Roughly equivalent to where I'm moving this. So I'm going to wrap this up here. This is actually at 2 hours and 20 minutes at the moment, so probably going to end up being about, hour and a half, or 2.5 hours-ish. I am going to get this updated and uploaded onto my website, so it'll, in the description of the video below will be a link to the files for this, if I recall correctly. Actually, you know what? Yeah, okay. So, what did I normally do here? It's been too long. I'm sorry. Basically, you're going to see a link to the download for this project. So all the code will be up on my website, so you can download it, you can play with it, you can expand upon it. I will put some instructions in there. So the things that you need here, so I'll put a README in here and say things you need, Pygame, Python 3.6 plus, not 2.6, 3.6 plus, Pygame, and that's it, actually. Python 3.6 and Pygame. So you can use pip install Pygame to get that. Or if you already have it, great. Or on Windows, it may be easier to install it. You probably already installed it on the other videos before you even got here, but there you go. I'll put this in there. So the files will be up. There will be a post on my forum, I think, for discussion, and I don't know, whatever other random things are normally in there. So for now, I appreciate it, guys. I'm sorry it's been so long in between videos. I'm trying really hard to make it a more frequent thing. I do have a baby coming in a month-ish, so woohoo! First kid. So unfortunately, that's likely to impact how often I can make videos, but I'm going to really make an effort to try and get these out more frequently. Please let me know in the comments below or on my forum what you would like to see. If there are things for coding games that you would like me to try and accomplish and do a tutorial on, or maybe it's like the Unity video we did before. It's not something I know, it's not something you know, but you're curious about it and you like the way that I explain things, feel free and mention it. If it's not something I know, I'll still do a video of me diving into it and seeing if I can figure it out and giving an honest opinion on how easy I think it is to get started. Not about whether it's good or bad or anything like that, but a get started thing. Kind of like with Unity, I really kind of like the idea of that. So hit me with your ideas. Have a great week. I will see you guys later.